we will move to the Hartley and Colpitts oscillator. We will also design the circuit by using transistors, not operational amplifier. Okay, so far we had seen RC based circuits, right? So we had seen RC phase shift oscillator. The feedback stage, we are using resistor and capacitor combination. Wien bridge oscillator, we use the resistor and capacitor in the feedback loop or the feedback stage. In crystal oscillator, we use crystal in the feedback stage or feedback loop. And the crystal, we know the equivalent circuit of the crystal. So it also has the inductor. So this crystal oscillator is not RC based oscillator. This is also RC. This is also RC. The crystal oscillator is LC oscillator. LC means what? Inductor and capacitor combinations we are using in the feedback stage. And Hartley and Colpitts oscillator is also LC type. So it's using inductor and capacitor in the feedback path. Okay, so now we will see this one. So there is a disadvantage of using basic LC oscillator because they have no means of controlling the amplitude of the oscillations. So same like the RC phase shift. So you have some idea what is RC phase shift. So let us just go back a little bit. So this is the RC phase shift oscillator, right? In the feedback path, I just directly used R and C network. Similarly, in the LC phase shift oscillator, if I use the L and C directly to create this kind of feedback stage, there are some issues. That is what I mentioned here. If you use the simple or the basic LC oscillator, then you cannot really control the amplitude of the oscillations. Even though you change the C value, you cannot really control the oscillations. So it's difficult to tune the oscillator to the required frequency. So we cannot use the basic LC oscillator if you want to really achieve the flexible oscillations at the output. So, however, it's possible to feedback exactly the right amount of voltage for constant amplitude oscillations by biasing the transistor amplifiers. So we will see the circuit now, then you will understand what does it mean. For example, if the oscillations increase in amplitude, the bias is increased and the gain of the amplifier is reduced. Let us see, this is the circuit. So this is the feedback circuit and this is the transistor. So you are controlling the biasing of this transistor by using this voltage divider R1 and R2, and also the feedback stage, the feedback circuit. So we are controlling the biasing. Based on the bias control, we can change the gain of this transistor. By changing the gain of this transistor, you can vary the oscillation at the output. So you can change the amplitude to higher or lower, but we want the stable oscillation. Let us see. If in this way the amplitude of the oscillations are kept constant using a process known automatic base bias. Here we are not applying any input. This is the Hartley oscillator circuit. We are not giving any external input. Everything is happening based on the thermal noise and it's producing the oscillations. So we have to be careful. If we want to change the oscillations, then where to touch, where to change the values if you want to achieve the different values in the oscillations. So that is why we have this, we have to have a careful design of this tank circuit. This is the feedback circuit. We will come to that now. So sorry. Okay, this is actually this feedback circuit. It's called self-tuning circuit or automatic base bias. We can call with different names, but the purpose or the working principle is simple and straightforward. So this LC oscillator, when we talk about the LC oscillator, we can say this, we are not going to use the basic one. So we need to make some changes in this basic one. We are not going to make the simple LC network. So we need to have some kind of special property in the feedback stage. For that, we are using these two different oscillators, that is called Hartley oscillator and Colpitt's oscillator. So we will see now how the circuit design of these two different oscillators that varies, that's different from the basic LC oscillator. So now first we will see the Hartley oscillator. Here we have the LC tank. So this is the LC tank circuit. This is the feedback circuit. So in any oscillator, we need a amplification stage and we need a feedback stage. This is the feedback stage of this oscillator. So here we have the two inductor. You can see this is the L1 first inductor and this is the L2 is the second inductor. And we have the capacitor in parallel. So you remember, you can notice the small difference here. I put the capacitor symbol and I put the arrow mark, right? So this is the capacitor and I put the arrow mark. So what does it mean? So it means this is the variable capacitor. So I can change the value of the capacitor by adjusting something. So in the lab next year, when you do the some more experiments, maybe in power electronics, you will see the load resistor. So load resistor is also variable load resistor. This is the resistor, normal resistor. If you put the arrow mark, then it means you can change the knob from here to here. You can move, and then the resistance value will be different. So this is a variable resistor, and this is the variable capacitor. So in the this is the circuit design of the tank, LC tank. So we have two inductors in series, and this one is connected in parallel with another variable capacitor. This tank circuit plays an important role to produce the oscillation. So by changing this C value, I can change the oscillations value. So LC tank circuit is connected between, did I finish here? Okay, so the Hartley oscillator design is using two inductive coils, L1 and L2 in series with a parallel variable capacitor C here to form its resonance tank circuit. This is the complete tank circuit that produces sinusoidal oscillations. In some circuits, L1 and L2 can also be a single taped coil. So instead of using two different inductors, we can also use a single taped inductor. So LC tank circuit is connected between the collector and the base of a transistor amplifier. So here we know this is the base of the transistor and this is the collector of the transistor and this is the emitter of the transistor. And this is in the common emitter mode configuration. So this tank circuit is connected between the base and the collector of this transistor. And emitter is connected to a tapping point of the tank circuit. That is the tank circuit. We can also call this as a tuned circuit coil. So just never mind this one, tank circuit. So this is the tank circuit. We have this central point, meeting point of these two inductors. This one is connected to this emitter. So this is the circuit construction, and we have this R1 and R2. The purpose of the R1 and R2 is for biasing this transistor. And we also have this R3 and C3. This C3 is the coupling capacitor. So it will block all the DC components, blocking capacitor, and it will only allow the AC signal and the oscillation. So because this is what we want, we do not want any AC noise in this output. So this is called blocking capacitor. And we also have, okay, we will see here one by one. When the circuit is oscillating, the voltage at collector here, this is the voltage. The voltage as collector is 180 degree out of phase with the voltage at the base. That is the property of this transistor. An increase in base voltage, if you increase the base voltage, it causes a decrease in the collector voltage, since the impedance of the collector load is resistive. So what does it mean? So I increase the voltage in the base, then what's happening? So it means I am turning on this transistor. So the transistor will be in the on mode. It means I am short circuiting this collector and emitter. So there's a current conduction is happening rapidly between this collector and emitter. So I increase this gate voltage, then because of this short circuit, whatever the voltage presence here, it will get reduced because this will just go down. So it is what mentioned here. The voltage at collector is okay. Of course, the transistor is giving 180-degree phase shift, and this feedback circuit is producing 180-degree phase shift. This is the standard, and we get 360-degree at the output. That is not a big problem. So now we are talking about an increase in the base voltage causes a decrease in the collector voltage because the collector is going down. Collector voltage is going down. And the impedance of the collector load is resistive. It's because of this impedance effect, but this is what happening here, this transistor. And the phase shift is not a problem that we know 180-degree, and we satisfy the Barkhausen criterion. This is okay. So the amount of feedback, so we are taking this feedback here. It really depends upon the position of the tapping point of the inductor. So here you can see the tapping point. So we are taking the, it's really depending upon the tapping point. So if this is moved near to the collector, then the amount of feedback is increased. So I told you I can change the base voltage. If I increase the base voltage, then what's happening? If I decrease the base voltage, then what will happen? If I decrease the base voltage, then this will be an open circuit. Then the collector current will be high. This is just like a switch. So you are giving this base voltage, and then you are making a connection or disconnection here between these two terminals. Okay, so this feedback, amount of this feedback voltage is really based on the tapping point of this inductor L1 and L2. So if I make this tapping point more close to this collector, this is the collector, right? So if I make this tapping point more close to the collector, then what's happening? Is more then the amount of feedback is increased. Thus the output taken between the collector and the earth is reduced. So output taken between, this is the output is taken, we are always taking the output from the collector. So this collector is reduced. Thus the output taken, okay, this is and the vice versa. Vice versa means what? So if you move this one down, then what will happen? Instead of putting here, I am moving away from the collector, the tapping point. So the opposite operation will happen. So if I move this tapping point again or more far instead of near, if I move more far from the collector, then the amount of feedback will be reduced. Here it's increased, so it will be reduced. Then what will happen here? When the amount of feedback is reduced, then the base voltage will be less, and then this will go off. The transistor will go off, and then, or at least it will be open circuit, and then the collector current will be something else. So we are changing the, this is what we want. So we want the voltage to move back and forth. So it goes to the peak, and then it goes down to negative, and then go to the positive peak, and the negative peak, and then positive peak, negative peak. So this is happening automatically. So we are getting the output at this collector point. So at this collector, we are getting this. So because of this natural operation, what is happening here, this base voltage will vary, and we are getting, because of the base voltage, there will be open circuit or short circuit, and then the collector voltage will go to the positive peak, and then it will go to the negative peak, and so on. That is the oscillation. And resistors R1 and R2 provide the usual stabilizing, that is the DC bias, this R1 and R2 of the transistor. So this is for the biasing stability of the transistor. We must need this R1 and R2. Capacitor act like a DC blocking capacitor. So this capacitor is blocking the DC components, and we are getting only AC at the output, sinusoidal. So that is how Hartley oscillator is working. So we have the feedback, and by changing this capacitor value, you can change the oscillations. What is the formula? The frequency of oscillation of the Hartley oscillator is F is equal to 1 divided by 2 pi square root of LC. L is the effective inductance. So we have L1 and L2. So they are connected in series. So it's very simple. Just adding this like this, where LT is equal to L1 plus L2 plus 2M. So you should know what is M. Here is something new. So LT is the total cumulative coupled capacitance if two separate coils are used in this tank circuit, and this M is the mutual inductance. So whenever you have some kind of two inductors, each inductor will have the magnetic field, electromagnetic field around the inductor, and there will be also some, because of this they are just overlapping each other, there will be some mutual inductance. So we have to also consider the mutual inductance effect when we calculate the total inductance value. So L1 plus L2 plus 2M. And this is the standard formula you should remember for Hartley oscillator and its frequency of oscillation. So frequency of oscillations can be adjusted by varying the tuning capacitor, that you know that variable capacitor, or by varying the tapping point. So you have two possibility to change the oscillations. You can change the capacitance value, or you can change the tapping point between this inductor. This one is the tapped inductor. So it means like I can move this tapping point up and down, either close to the collector or far from the collector. Also, it gives an output over a wide range of frequencies, making it very easy to tune. So it means this Hartley oscillator is very dynamic. You can change the frequency of oscillations to wide range. You can have, for example, 1 kilohertz, or you can have 1 megahertz. By just changing this tapping and this variable capacitor, you can change the value. So that's a good in a way. So you can use this oscillator in different applications. Also, Hartley oscillator produces an output amplitude which is constant over the entire frequency range. That's correct, because we want only sustained oscillation. We do not want damped oscillation that we had seen in the last lecture. What is damped and what is sustained. So we can have a sustained oscillation.